this part of our discussion will now concentrate on discussing how to sketch a curve that is defined parametrically for us. Like in example 1, they're asking us to sketch the curve that is described by the following parametric equations. This is the parametric equation for x and this is for y. And if you look at t is now between -2 and 3. When I begin analyzing the curve, I like to begin by just analyzing each equation separately. And I like to think of the equations in the normal rectangular form, the old way of thinking about graphs. I think of t as my input, I think of x as my output, what typically represents y. Here is where I am going to sketch the parametric curve, but that curve is going to come much later. Right now, let me analyze this in the traditional sense. So in the traditional sense, I think of t as my ordinary input. So t is going to be along the horizontal axis. And I think of x of t as my output. So that's going to be on the vertical axis. And if you notice, in the traditional sense, that would be a quadratic opening upwards. So the graph would actually go like this, right here. And this would be -4. That's where the vertex of that parabola will be located. However, I am not going to be using the entire parabola because I do have a restriction on t. T is between -2 and 3. So then, let me quickly figure out what is x of -2. X of -2 will be equal to -2 squared, so that's going to be 4, minus 4, 0. That means that we are going to be right here, this part of the graph here. And then t is going to go from -2 all the way to 3. So when t is equal to 0, we are here at -4. When t is equal to 3, we are going to have 9 minus 4, which is going to give me 5. So that's going to be randomly, just let's say somewhere there. So the part of the graph that I really want, let me erase, is it possible? 1 second, will be, it's not erasing. Okay. It is going to be just this part right here and this part right here. So this is the portion of the graph of my, that will represent the x values of my parametric curve. That means that this is telling me that x, the x values, if you notice, the x values, remember that the x values are now being measured on the vertical axis. The x values are going to go from -4 all the way to 5. This, when t is equal to 3, the output is 5. So then the x values of my parametric curve will go from -4 to 5. And I'm going to make a note of that. I already know that all of my x values, I'm repeating myself, are going to go from -4 all the way to 5. This is going to be observation number 1. Then, in the same way, I am going to go ahead and analyze the second equation right here. And if I do that in the traditional sense, I will have t here, I will have y right here, and then t over 2 is linear. That graph is going to go somehow like this. But then again, because t is restricted, t is between -2 and 3, I'm only going to be using a certain portion of my graph. In fact, y of negative 2 is going to be negative 2 over 2, so that will be negative 1. So when t is negative 2, the y value is going to be negative 1 right here. This is telling me pretty much that I will not need this part of the graph, so I will erase that. Then y of 3, going to the other extreme, will give me 3 over 2. So when x is 3, the y value will be 3 over 2. That means that I'm going to go ahead and erase this part of my graph. So then the y values of my parametric curve are going to go from negative 1 over here all the way to 3 over 2. I want to go ahead and make a note of that. I know that from negative 1, that will be less or equal than y, and y is going to be less or equal than 3 over 2. That means that y is going to be between negative 1 and 3 over 2. And these conditions for x and for y is exactly what I should notice happening here in that parametric curve. So now that I have a sense as to where x is going to be and where y is going to be, I am going to generate a few points here. I'm going to create a table of values. So if you notice, I've chosen values for t when t is equal to 0, 1, 2, and 3. I am going to plot 0 into the equation for x, and then 0 for the equation for y, and I should get that when t is equal to 0, x is going to be equal to negative 4, and y is going to be equal to 0. When t is equal to 1, x will be negative 3, and y is going to be equal to 1/2. When t is equal to 2, x is going to be equal to 0, and y is going to be equal to 1. And when t is equal to 3, when t is equal to 3, x is going to be equal to 5, and then y is going to be equal to 3 over 2. So I already generated several points on my curve. The first one is the point negative 4, 0, then negative 3, 1/2, 0, 1, and 5, 3 over 2. Now I can continue in the same way, plugging the value of t, negative 1, into my parametric equations, and I can get my other point here. And t is equal to negative 2, same thing. I plug negative 2 into here, and I get my other point, my last point. But I also want to show you how to think a little bit more efficiently, and that is by using symmetry. Sometimes using symmetry can really help you determine the shape of the graph in a more efficient way. For example, imagine that I consider negative t and I plug this in the expression for x. So I have x of negative t equals negative t squared minus 4. This equals to t squared minus 4, and immediately I notice that this became the same thing as x of t. So what I notice is that x of negative t is identical. X of negative t is equal to x of t. So the x values are the same for negative t and positive t. That means that immediately I can determine what is going to be x of negative 1. X of negative 1 will be identical to x of 1. The x value will not change when t is 1 or when t is negative 1. So x of 1 was negative 3. that means that x of -1 will also be -3. Same thing with t equals -2 right here. I know that x of -2 will be identical to x of 2. What is x of 2? X of 2 is 0. So here I am going to have 0 as well for the x value. Now, what happens with the y values? What happens if I consider y of -t? If I consider y of -t, I am going to have -t divided by 2. And this part over here is y of t. So this will be negative y of t. What is my conclusion then? Conclusion is that y of -t is not exactly equal to y of t, but is equal to the opposite of y of t. If you think of the graph, that really means that the graph will be symmetric about the x-axis. And with this in mind, I can now determine the corresponding y values for t equals -1 and t equals -2. Let's do t equals -1. I already know over here that y of -1 will be equal to minus y of 1. And what is y of 1? Y of 1 is equal to 1/2, so then -1/2. I'm going to go ahead and put over here -1/2. And then y of -2 will be minus y of 2. So then that's going to be minus, and y of 2 was equal to 1. That means -1. So over here, we're going to have -1, and that already gives me another set of points. So I'm going to have -3, comma, -1/2. And then over here, I am going to have 0, comma, -1. When I sketch my curve, I already expect to see that my curve is symmetric about the x-axis. The x values of every point will be the same for positive and negative t's. And then the y values, though, are going to be opposite in signs. Let's go ahead and begin plotting the points. The largest x value that I have is 5, and the smallest x value that I have is actually -4. So I'm going to go 1, 2, 3, 4, and 5 right here. 1, 2, 3, and 4. And then maybe along the y-axis, I can make 2 marks, the equivalent of 1, and then 2, 3. And same thing over here. So this will be 1, 2, this will be -1. All right, so the first point will be -4, comma, 0. Let me plot that point over here. Then 1, 2, 3, so -3, comma, 1/2. That's going to give me this point here, 0, 1. And then I'm going to have 5 and 3/2 right here. Then I will have -3, comma, -1/2. So that's going to be this point right here. Again, notice how the x value is the same, -3, but then one of the y values is +1/2 right here, and the other y value is the opposite, -1/2. And that's the pattern. We were expecting that. Then we're going to have, when x is equal to 0, y is going to be -1, so that's going to take me here. And this is practically the shape of my graph. Is a parabola that opens along the x-axis. Let me draw that a little bit nicer right here. So right there, that's my parabola. And it's just opening again along the x-axis. It is inverted in a sense. So again, you notice how the x values, look at the x values, they go from -4 to 5 as we expected. And then the y values are going from -4, -1 all the way to 3/2 right here. So these are the y values. And that was again already expected. And we can see the reflection, right? This part, the upper part of the parabola, notice how it is perfectly reflected about the x-axis right here. If you were to fold this grid about the x-axis, the upper part should match nicely with this part over here. And the parabola doesn't go off forever to the right, and that's because t is restricted. T is between -2 and 3. Now, the direction. We have to specify direction. In order to specify direction, I like to begin with my negative t value. So from -2, -1, 0, 1, 2, and 3. So I like to think of beginning with the outermost negative t value to the outermost positive t value. And let's see what happens here. When t is -2, so this is practically going to the bottom of my table. When t is -2, I am right here at 0, -1. Then when I transition to t -1, so when I go upwards to -1, my y value moves to -3, -1/2. So look at this. I already went in this direction. In fact, let me put a little arrow. I went from here to here. But let me continue with a few more points so that I get the right direction. I want to make sure that I specify the correct direction. So when t is equal to 0, the point was -4, 0. That means that we're here. When t is equal to 1, the point is -3, 1/2, right here. So it seems as if, indeed, we continue to move in this direction. Then when t is equal to 2, the y value is, the coordinates, are 0, 1. So the point is here. And then when t is equal to 3, the point is now at 5, 3/2. So then indeed, this particular bug moves in this direction. If you remember our cute little bug right here, it started here and then it moves in this direction along the graph and it continues to move right here. And then it will stop there because t can go as far as 3. So here we have the graph of a function that was expressed parametrically. But before I end this discussion, I just want to go ahead and on the graph next to each point, write its corresponding value for t. This is something very typical in these type of graphs. So for example, when we start our journey, we start right here on the negative x, the negative y-intercept. So that point corresponds to t equals -2. Then this point over here corresponds to t equals -1. Then this one here corresponds to t equals 0. Then this one corresponds to t equals 1. This one corresponds to t equals 2. And finally, this one corresponds to t equals 3. And now the diagram is complete. With t equals 0. In example 2, they're asking us to sketch the following curve described by the parametric equation where x of t is equal to sine of t, y of t is equal to sine squared of t, and t can be any real number. And just like I did with example 1, I'm going to go ahead and examine each of these parametric equations separately in the old-fashioned way. So doing that, let's look at the first one. This is going to be my typical plane where t is the input, x is the output, so it's going to go along the vertical axis, and this is just sine of t. So I know that sine of t oscillates back and forth between -1 and 1. All right, this is a bad sinusoid. Let me continue like this. Okay, and then the same thing over here. Pretend it's beautiful. So the lowest value is -1. The highest value is going to be +1. This is telling me that the x value of my parametric curve is going to be between -1 and 1. So I am going to write that down. I already know that -1 is less or equal than x. X is less or equal than 1. So again, when I go to sketch my parametric curve, the x value of that graph is just going to be between -1 and 1. Now, doing the same thing for y. We will have the regular plane. Here we're going to have t. Here we're going to have y. And because you notice here that sine is being squared, practically everything that is below the x-axis is going to be reflected upwards. That means that the curve should behave like this, something like this. And the same thing over here, something like that. So when I look at this graph, I see that the lowest y value achieved will be 0 and the highest y value achieved will be 1. So I'm going to go ahead and highlight the interval for the y values of my parametric curve. And I'm going to even make a note of that. I am going to note that 0 is less or equal than y, and y is less or equal than 1. Now let's investigate symmetry. We're going to start with the expression for x. We know that x of t is equal to sine of t. So then we're going to go ahead and see what happens whenever we consider x of negative t. X of negative t will be equal to the sine of negative t. But because sine is an odd function, then that means that by definition of an odd function, this negative is going to come in front of sine. So then this is going to be equal to negative sine of t. Well, immediately we notice that this part right here is x of t. So then we are going to end up having that this is equal to minus x of t. When we now put this together and this right here, what we notice is that x of negative t is equal to minus x of t. So let's take an example here. Let's pretend that t is equal to 3 seconds. What we really have is that x of negative 3 is going to be equal to negative x of 3. So let's analyze this for a second. What we are saying is that x of negative 3, the value of x of negative 3 is going to be equal to minus the value of x of 3. So definitely something to keep in mind. What we're going to do now is to do a similar analysis on y, and then we're going to put everything together. We know that y of t is equal to sine squared of t. So if we consider y of negative t, that will be equal to the sine squared of negative t. I am going to rewrite this though as sine of negative t, all of it squared. And then again, knowing that sine is an odd function, I can re-express that inside as negative sine of t. But then because I am squaring, then that means that this negative is going to disappear. And that is going to give me sine squared of t. So what I notice is that sine squared of t is again y of t. Putting the beginning together and the final answer together, we conclude that y of negative t is identical to y of t. How interesting. So then let's put everything together. The x values of this curve we know are given by sine of t, and the y values are given by sine squared of t. This is how an order pair is going to be built. But then if we now consider negative t, what we really found is that for negative t, the x value just becomes the opposite of sine of t. And then the y value actually doesn't change, right? It stays the same. So this is over here for just t, and this is over here for negative t. So again, when we consider a t, this is how you get the coordinate point. And this is exactly what we're going to go ahead and do here on this table. But whenever you consider the opposite of t, negative t, like let's say 3 versus negative 3, the x value will be the opposite of what you get here. So it's going to be on the other side of the y-axis. And the y values, the height, doesn't change, the height of that point. So if you try to think about what is happening here graphically, what you really notice is that by changing the x value to the opposite of, let's say, the original one, and by not changing the y values, this graph then is going to be symmetric about the y-axis. Whatever happens on the right of the y-axis is going to happen on the left of the y-axis. In the previous example that we did, example 1, we had symmetry about the x-axis. Whatever happened above the x-axis pretty much happened below the x-axis. And here is the other type of symmetry. So whenever we start building the parametric curve, we should already expect symmetry about the y-axis. Moving to the table right here, you notice that I already completed the first part of the table. I completed the part where t is positive. And because every time that we work with trigonometric functions, we will continue using radians as the measure of our t, then I took the special type of angle so that it would be easy for me, and that way I could avoid trying to use a calculator. If you notice, I considered 0, pi over 6, pi over 3, pi over 2, 2 pi over 3, and this is random. Practically, you can choose any value that you want, but I wanted to stick to very nice values for t. And I went all the way up to 7 pi over 6. I substituted all of these t's over here, and then I did my algebra. And you can do this in the way that you were taught last year in grade 12. You can use special triangles, you can use the unit circle to figure out these values here. Now for the bottom one, I could go back and do all that algebra, pretty much repeat the algebra for negative pi over 6, negative pi over 3, but I want to be more efficient. If I already know that this graph is symmetric about the y-axis, then pretty much I can immediately start filling this part of the table here without doing too much work. Please remember, going back here on the left, the x values are that you have sine of t, and then in the other case, for negative t, the x value becomes negative sine t. So then that makes this quite easy here. Pi over 6, let's do the first one. I skipped 0 here in the bottom because then nothing would change. So let me start with negative pi over 6. I will compare that to pi over 6. So I know that for negative pi over 6, the x is going to be the opposite of what I have here. So it is going to be, if I have 1/2, here I'm going to have negative 1/2. And then the y values are not going to change. So if I have 1/4, here I'm going to have exactly 1/4 all over again. So 1/2 will go to negative 1/2, and then the y value remains the same. When t is equal to negative pi over 3, the x value will be negative root 3 over 2, and the y value will stay the same. For negative pi over 2, we're going to go from 1 that we had before now to negative 1, and the y value will be 1. So hopefully you now get the point. So I'm going to finish this a little bit faster. Negative root 3 over 2, 3/4. And then negative 1/2, 1/4, 0 and 0. Then on the last one, because I have here negative 1/2, here I'm going to have negative 1/2. So then that's going to turn it positive 1/2, the opposite of what I had before, but the y value remains the same. So now pretty much I have all of my coordinate points on the upper table and coordinate points on the lower table. What I have to do now is to go ahead and plot those points. I don't think that you need to see me plotting points, so I'm going to go ahead and do that and just come back here with the actual curve on the xy plane. I want you to notice here that I came and I plotted all of the points that we had in the previous table, all of those points over here, and then this is what I ended up getting. I ended up getting something that looks like a parabola, but it doesn't extend forever, and that's not surprising. It shouldn't be surprising to us. If you remember over here, this is what we investigated before we started the sketching process. We found that x was going to be between negative 1 and 1. And if you notice, this is exactly what is happening over here. X is between negative 1 and 1, and it stays between negative 1 and 1. And y is between 0 and 1. You can see it over here as well. Y stays between 0 and 1. No matter what t is equal to, y stays between 0 and 1. And we also discovered that we were going to have symmetry about the y-axis. And this is what you're noticing here. Whatever happens on the right of the y-axis happens on the left of the y-axis. So far, everything matches with what we developed last time. The only thing that we have to do now to finalize this question is to investigate that direction of movement. Again, if I have my bug moving along the graph, I want to know how that bug is going to move. Just as we did in example 1 to investigate the path of the bug, I like to go from the smallest t-value all the way up to the right, to the positive, to the largest t-values. So from negative 7 pi over 6, I want to be able to go to -5, -5 pi/6, and pretty much keep track of the movement of the points as I increase in t values. So again, we're going to go ahead and begin with -7 pi/6, and we're going to move in that direction. So practically, we're going to be moving upwards, and I'm going to be tracking the flow of the points. So let's see what is happening. Starting with -7 pi/6, the point was at 1/2, 1/4. You can see it right here. Let me even trace that point again in red to keep track of kind of the beginning there. Then when I go to -pi, the point now becomes 0, 0. That's the origin. So it seems as if my first red point is now moving down towards the origin. Interesting, but let me take a look at a few more points. When I now go to -5 pi/6, the point becomes -1/2, 1/4. So now again, it continues moving towards the left. So I think that it's time for me to put arrows. So I already noticed a behavior like this. And then when I continue with -2 pi/3, the point becomes -√3/2, 3/4. So then that becomes this point over here. So again, as if the bug continues to move in that direction. And then when I move to -pi/2, the point becomes -1, 1. So we are right here at the very top. So this point, or this bug, continued to move in that direction. Let me try a few more t values. I want to really be sure about the direction of motion here. Then when I transition to the positive t values, if I am at -pi/6, the next one will be 0, right? Because we want to be able to go in order. From -7 pi/6, we're going to -pi, -5 pi/6, we're getting closer and closer to the origin. So let's move all the way. Once we get to here, let's go to 0. And then when t is equal to 0, we are back at the origin. How interesting. So from -1, 1, which happened at -pi/6, we are now back over here, the bug has moved all the way down to the origin. And then at pi/6, the point is going to be 1/2, 1/4. So now from the origin, we go to 1/2, 1/4. And then at pi/3, √3/2 and 3/4. So now we're going here. At pi/2, 1, 1. Then at 2 pi/3, we are now going down to 3/4. And then we're going back to the origin. And then we're going here. So then what is really happening here is that pretty much the bug is moving, let me try it like that, down, down in this direction, and then the bug comes back in the other direction, and back. And no matter what t is equal to, this bug keeps moving back and forth, back and forth, back and forth. So here is my bug right here. So the bug moves down and it goes to this point, then it gets bored and it comes back up. Then it gets bored again and it goes back up. It's just like rocking itself on the curve, bouncing back and forth, back and forth. Remember, t is infinite, but this bug never stops rocking back and forth. Okay? So let me push him aside. All that I want to do now is to specify a few t values next to their corresponding points. I am not going to go ahead and write down every single t value. There are just too many and it's going to get too messy because again this bug keeps moving back and forth like that. But at least to guide the reader as to which point corresponds to what t value. So just something as a guide. So this point over here, I'm going to start with this tip over here on the right. That point corresponds to t equals to pi over 2. Then this one right here going down on the graph, that corresponds to t equals pi over 3. And then this one corresponds to t equals pi over 6. I'm just looking at my graph. And then the origin corresponds to t equals 0. Let's do some of the negative values. So this one right here will correspond, so negative 1/2 and 1/4 to t equals negative pi over 6. And then this one right here will correspond to t equals negative pi over 3. And let's say this one right here, negative 1/1, corresponds to t equals negative pi over 2. And again, in order to determine this, I was just consulting the table here on the left and paying attention to the coordinates on the graph. So mostly by just looking at the table, I can determine the corresponding t values for every point. Example 3 is asking us to sketch another parametric curve. This is the curve that we're going to be sketching. The only difference here is that the values for t have been chosen for us. That's okay. That will just make things a little bit easier for us. So these are the t's that we're going to consider. And if you notice over here on the table on the right, I already have those t's. Here are the positive t's and here are the negative t's. And t squared plus 1 is the x component of the curve, and t to the third minus 4t is the y component. And just as in the previous two examples, the first thing that I'm going to do is to analyze in the traditional sense the graph of x of t and the graph of y of t, because I want to be able to know the interval for the x values and the interval for the y values before I sketch my curve. And then after that, I will see if there's any type of symmetry in this particular graph, because that's also very helpful. Here I have the graph for x of t. So the graph here is a parabola, and that's because x of t is t squared plus 1. Notice again how I positioned t along the horizontal axis, and then x goes along the vertical axis. So what I notice immediately is that the x values will go as low as 1, and then they will grow all the way upwards. So pretty much what this is telling me, and I want to make a note of that right here, is that x is going to be greater or equal than 1. So x will be greater or equal than 1. So when I sketch my parametric curve, I will see that the domain of that curve will be all x values that are greater or equal to 1. Here on the right, I now have the graph for y of t. Y of t is equal to t to the third minus 4t. It's a beautiful polynomial that exhibits a positive end behavior on the right of t and negative end behavior to the left of t. In fact, you know that there should be arrows on top and arrows below. Same thing here on the left, arrows on top, arrows below. So what I notice now is that all the y values in this graph pretty much will be or will consist of every single real number. So what I will take a note of is that y pretty much can be any real number that you can think about. So fantastic. The domain of the graph will consist of all x values greater or equal than 1, and the range of my graph or my curve will consist of every single real number. It's going to be infinite in both directions. Now on to symmetry. To begin the analysis of symmetry, we're going to begin in the same way as in the last two examples. We're going to start with x of negative t. Substituting that into x of t, that will be negative t squared plus 1, which is going to be t squared plus 1, which is going to give us x of t. So I notice over here, when I put the end and the right end together, right here, I notice that x of negative t is equal to x of t. How interesting. So practically this is saying that if t is equal to 3, for instance, x of negative 3 will be identical to x of 3. So the x values with t and negative t do not change. Now for y, same thing. Y of negative t is going to be equal to negative t to the third minus 4 times negative t. That is going to be negative t to the third plus 4t. I'm going to go ahead and factor a negative out. So then that's going to give me t to the third minus 4t. And if you notice right here, this is the original expression. This is actually y of t. So then we have here that this is going to be equal to negative y of t. Again, putting the beginning and the end together, this is telling us that y of negative t is minus y of t. So what I notice right away is that the x's don't change. X of negative t is identical to x of t. But the y's do change. Y of negative t is equal to minus y of t. That means a reflection about the x-axis. So this graph is symmetric about the x-axis. The x's remain the same, but the y's are reflected about the x. The y's will be y of negative t, and then the other one will be the opposite of y of t. So this graph will be reflected about the x-axis. It's going to exhibit symmetry about the x-axis. So the portion above the x-axis should match up nicely with the portion below the x-axis if you imagine folding a sheet of paper about the x-axis. So we should expect to see that. So let me write that down. We should expect to see a reflection, or let me say symmetry, about the x-axis. I already started filling out the table here for the positive t values. Again, when t is equal to 0, you're going to go ahead and plug in 0 here, 0 and 0, practically wherever you see a t, and then you're going to have your x and your y value. Same thing with t is equal to 1 and 2 and 2.5. For the negatives, I will take advantage of symmetry. I can go ahead and plug in negative 1 here, negative 1 and negative 1, and I can get my values, but I want you to start thinking a little bit more maturely when it comes to sketching graphs. You already know that this graph is symmetric about the x-axis, so use that to move a little bit faster. So in that case, when t is equal to negative 1, we already know that the x value will stay the same as 2, but then the y value will be the opposite of what we had before. So then that's going to be positive 3. Then negative 2, x will stay the same, and 0 won't change because negative 0 is 0. And then for negative 2.5, 7.25 will remain being the x value, but the y value will be negative 5.625. And then in the next discussion, I'm going to go ahead pretty much and start plotting these points. Here you can see again the table from the previous discussion, identical table. I've started sketching already on the XY plane because now I am sketching the parametric curve. I started sketching the upper part of the table just with the positive t values, and this is what I have right here. So then practically this point right here corresponds to t equals 0. This one right here corresponds to t equals 1. This one t equals 2. And this one right here t equals 2.5. And you can notice that the graph shapes up like this. Notice how the x values begin at 1 and then they seem to extend in this direction. The y values will continue extending towards positive infinity. What I have to do now is to do the bottom part of the graph. I have to sketch those values, but then I know that whatever happens below is going to happen above. Whatever happens above is going to repeat below because of the symmetry about the x-axis. So that makes everything so much nicer. Okay, so moving on to those values, the point on the x-axis will stay on the x-axis, but this point right here, it is going to be reflected 3 units upwards. That means right here, the x value doesn't change, but the y value is the opposite of what it was before. This point over here will stay there, and this point is going to be reflected downward. So I think it was negative, it should be negative 5.6. So 1, 2, 3, 4, 5. Negative 5.6 will take me, say, somewhere there. And then sketching my graph, I am going to have, it should be identical to what I had before, something like this, okay? And that becomes my graph. So this value right here happens when t equals negative 1, we said. This one happens again when t equals negative 2. And this one here when t is equal to negative 2.5. The last thing that we have to do now is to track the movement of our bug. And as always, I like to begin that exploration by starting with the starting from the left of the t values all the way to the right. So from the outermost negative t value all the way to the outermost positive t value in our table. So I like to work backwards in this direction. So just like this, for instance. So I'm going to start with negative 2.5 is what I'm trying to say. Following my graph and looking at my table, I'm going to be working with the 2 at the same time. When t is equal to negative 2.5, if you remember, we were right here. In fact, let me mark that dot in red. I'm thinking of this as my beginning, for instance. So we're here. And then we will continue with negative 2. When t is equal to negative 2, here is t equals negative 2. Notice how we seem to be moving in this direction. I'm going to go ahead and immediately start drawing my red arrows. And then continuing with -1, now -1 takes me there. So as if my particle crosses through the x-axis and now goes to this little high point right there. So again, I want to keep track of my movement, so I'm going to put arrows. And then we're going to continue with t equals 0. That takes me down. Then after 0, we're going to go ahead with 1. So that is taking us to the top of the table. When t is equal to 1, we're here below. So let me start writing or drawing my arrows. And then continuing with 2 and 2.5. When t is equal to 2, here is 2, we are back on the axis, so the particle or the bug is going to turn around. And then when t is equal to 2.5 is here, and it continues its journey forever upwards. So here, here, and here. So here is my cute little bug. Let's say that he's practically coming from the negative infinity. He's moving along the graph. He turns around a cute little loop, and then he continues its journey all the way upwards. Notice again how this curve is not a function, right? In this region, it fails the vertical line test. So you couldn't find a single rectangular expression for this curve. You couldn't find f of x equals in some expression in terms of x. It's not a function here. However, parametrically, we were able to find an expression for the x component and for the y component. T was pretty much any real number. And then you can sketch a beautiful, beautiful graph right here, a nice curve. Here I have a brief summary of all 5 steps that I kept taking pretty much in examples 1, 2, and 3 when sketching parametric curves. If you notice, the first thing that I would do is to sketch x of t and y of t in the traditional sense, thinking of t as being on the horizontal axis and x or y as being on the vertical axis. In doing so, I was able to get information about the conditions for x and for y. Then in step number 2, I would analyze the symmetry of the curve by computing x of -t, y of -t, and then comparing it to x of t and y of t. Even though in the 3 examples that I did here for you, I ended up getting some sort of symmetry, please know that this will not always be the case. Sometimes you're going to have curves, you're going to examine x of -t and y of -t, and you'll find nothing interesting. But I showed you 3 examples where symmetry was particularly nice. Step number 3 was to construct a table of values. I would start by doing a straight substitution with the positive t values, right? You take the t values and you substitute them into the x expression and the y expression, and then that's how you get your coordinate points. And then I would use symmetry, knowledge from symmetry, in order to fill the table for the negative t values. Now, if the curve is not symmetric at all about the x-axis or the y-axis, then you're going to have to do straight substitution with the negative t values as well. Then step number 4 was now to sketch the parametric curve. I already had all of the order pairs from the table. I would just go ahead and sketch those points on the xy plane and then connect them with a smooth curve. And then the 5th step was tracking the journey of our bug. We needed to determine the direction of motion of the curve. So in order to do that, you remember that I like to take my t values and start from the smallest t value on my table all the way up to the largest t value. And then in that way, I can track down the motion of my bug. Then I would draw little arrows on the curve so that the motion is visible. And then next to each point, I write down the corresponding t value. So 5 steps that we can follow whenever we need to sketch a parametric curve.